Hello guys. In this video, we will understand the inner workings of an LSTM RNN block in detail with complete math involved. I will take some examples on computations involved in it, so you will understand how it is successful in preserving the long-term context. Okay. So this video is going to be a long one, as I'll try to simplify the stuffs involved in it. It may take around 45 minutes to 1 hour, so please listen to it carefully till the end. If you have watched my previous videos on LSTM part 1 and part 2, I would suggest you to first watch those videos and then start with this particular video, okay? Because those two videos will set the base for you to get started with the detailed explanation, okay? So without wasting much time, let's get started with this part. So you have already seen a figure of LSTM, right? So this is a LSTM RNN block. I will quickly refresh you guys on the components involved in it. Okay, so we have an additional component which we call it as a cell state or memory cell, right? So that is represented with the help of C t minus 1 C t here at time step t, and this is at time step t minus 1. So this is called as cell state or memory cell. Okay. Then we have the activations from previous time step at minus 1 here, and at this particular time step at, and this is the input at time step t, that is xt. So usually I represent it as xt. Okay. And then we have the gates. I had told you, right? So we have totally 3 gates. So this is the first gate. This is called as forget gate. This is the second gate. This is called as update gate, or also called as input gate. Okay, you can call it by whatever name you want. And this here remaining stuff is called output gate. Okay, so these are some of the components. Now the small boxes you are seeing here highlighted in yellow, which I am highlighting it here, right? So these are all the hidden layers. So how many we have? We have 4 hidden layers. Let me just write it down. In LSTM block, we have 4 hidden layers, and all of these are neurons. Okay, so each of these layers have the neurons, and these are all separate layers. They are not connected to one another. Okay, so forget gate has its own hidden layer with its own set of neurons. Update gate has its own set of neurons in its hidden layer. Output gate has its own set of neurons in its hidden layer. Okay, and you have 2 hidden layers associated with the update gate here. I will explain it in a while. And this final one is with respect to the output gate. Okay, so it has its own set of neurons associated with it. Okay, now we have some operations here which is represented as multiplication and encircled around that. So this is called as pointwise multiplication. Pointwise, or you can also call it as element wise. So the actual technical name for this is Hadamard. It's called as Hadamard product. Okay. And whatever symbol you are seeing it here with the plus sign encircled, it is called as pointwise addition. Pointwise addition or element wise addition. Okay. So the symbol multiplication encircled is called as element wise multiplication or point wise multiplication, or it is also called as Hadamard product. And this symbol is associated with an operation called as element wise addition. Okay. Now I will go slowly so that you will not be confused. Okay. So I will tell you what do we mean by pointwise addition and pointwise multiplication with some example. So let's say we have 2 matrices. Okay. So 1, 2, 3, 4 and 5, 6, 7, 8. So we have these 2 matrices. So if we want to have the point-wise or element-wise multiplication, or in other words, Hadamard product, what we will do? We will multiply the corresponding elements. First element in the first matrix with the first element in the second matrix, second element in the first matrix with second element in the second matrix, so on and so forth, right? So we will multiply this. 1 into 5, 5, 2 into 6, 12, 3 into 7, 21, 4 into 8, 32. So this is the Hadamard product or point-wise multiplication of two matrices. Okay. So what is this point-wise addition? So again, if you take the same matrix example, 1, 2, 3, 4, point-wise addition with 5, 6, 7, 8. So we just add up the respective numbers there at their positions. So 1 plus 5, 6, 6 plus 2, 8, 3 plus 7, 10, 8 plus 4, 12. So this is the result of point-wise addition. Okay, hope this is clear. Now coming to the main thing. So I told you about the gates, right? So before actually going into it, we will stick to some assumptions. So what are those assumptions? Let me quickly write it down. I'm writing these assumptions just for the clarity, right? So that I can explain you guys with some example and also make sure that the matrices shape are in order. Okay. So what are the assumptions? Let's say hidden layers. Let's say we have 4 neurons in each hidden layer. Okay. So in LSTM we have 4 hidden layers. Each of the hidden layers will have 4 neurons. Since hidden layers has 4 neurons, the activations AT minus 1 and AT will be of shape 4 cross 1. Okay. This is also called as a vector of 4-dimensional vector. Okay. Then we will have our input xt. Let's take we have 5 features in it. Okay. So let's, for example, for simplification, let's say we have 5 features in our input. Now we have something called as this ct and ct minus 1, right? So let's say this will also be of the same dimension as of activations. Okay, so that's the compulsion with respect to LSTM. So this is also a vector of 4 dimension. This is a 4-dimensional vector. Okay, so please be clear on these assumptions on the shapes of each of the vectors. So these are all vectors. Okay, now coming to the gates one by one. So this gets interesting from here onwards. Please listen to it carefully. Okay, now this entire figure has been subdivided into 3 parts. Okay, so let me just highlight it. So this is forget gate. This here it is update gate, and this part here it is output gate. So I will give you the link of the blog where we have these diagrams, and also it has a beautiful explanation. You can go through that. I'll give that link in the description. Okay. So now let us start to understand the gates one by one. Okay. So first about this forget gate. Forget gate. So as I told you in my part 2 of LSTM video, it helps in either completely removing or partially removing or not at all removing the previous cell state. So whatever we have from the previous cell state or the memory cell CT-1, this helps in either forget everything from that, or forget only few things. You can call it as partially forget few things, or not forget at all. So we want this information to flow as it is if we do not want to forget. So this forget gate has the ability to deal with these 3 things. So if we want the previous state context to be passed as it is, it will help in that case. If we want it to forget few things, it will also help in that case. If we want to forget everything, this will help in that case also. Okay. So how it will help? Let's see. So you can see here, you can in this figure, this is ft, right? So for my explanation purpose, I will call it as gate. Since we are dealing with gate, right? So let me denote f as g and forget gate as f. So G stands for gate and F for the respective gates. Okay. So GF forget gate, GU update gate, and GO output gate. Okay. So this is what my naming conventions will be while explaining this video. Okay. Now each of these gates will have their own weights associated with them. So forget gate will have WF, sorry. Okay. Update gate will have its own weights associated with it. We'll call it as WU. And output gates will have its own weights associated with it. Let's call it as WO. Okay. Since these all are separate neural networks, they will have their own weights and biases associated with them. Also, we'll have the biases W, just like WF, BS stands for bias associated with forget gate, bias associated with update gates, BU, bias associated with output gates, BO. Okay. Now let's come back to our forget gate here. So if you see the figure here, so it clearly states, and one more thing to remember, this ht minus 1, in my case I am calling this as A. Instead of h, I am calling it as A, t minus 1. Okay. So I am just maintaining the consistency as I told in my earlier videos. A t minus 1, this will be AT. Same way here, AT minus 1, AT. Okay. So just for maintaining the consistency. Now, how are we calculating this gate here, GF? So if you can just look at the, just a minute guys. Okay. So if you can just look at this particular part here, we are getting inputs for this forget gate. What are the inputs for this forget gate? Activation from the previous state, AT minus 1, and input at the current time step T. Okay. And we are applying sigmoid activation function. So what are the weights associated with this? It will be WF, because we are dealing with forget gates, right? So let us compute the output GF, how it is there. GF, the forget gate, is equal to sigmoid activation function on WF into A t minus 1 comma xt plus the biases associated with it will be BF. Okay, so this is what the computation for forget gate looks like. Now let us think about the dimensions and understand them in a clear way. Now this representation here is nothing but stacking the features together from the previous state activation and the current state input, current time step input, that is xt. So we know that activations are of 4 dimensions, right? So these are our A's, and xt has 5 features, right? So this is how the connection looks like. Since this is a neural network, the hidden layers are neural networks. So how this looks like? So we are stacking this xt 1, 2, 3, 4, 5 features, and then 4 features of A t minus 1, right? So if I can just represent this, this is xt and this is A t minus 1. So what we have next, we have this is our fully connected neural network, right? So I told you these are neural networks, hidden layers, right? So we will have the hidden layers, and the hidden layers are of size 4 neurons, right? So we will have 4 neurons associated in the hidden layer, and this is a fully connected layer. So you guys know what fully connected layer is. So every neuron in the input layer is connected to every other neuron in the hidden layer. So I'll just draw it for one. You get the idea for rest of these 3 neurons in the hidden layer. Okay. So it will take time for me to draw. Let's not waste time there. Now, the weights associated with it is called as WF. Right. So what will be the shape of this weight matrix? It will be 4 cross 5 plus 4, 9. So this will be the dimension of weight matrix F. So we have got this. So let me just write that formula again. Sigmoid of WF AT minus 1 comma XT plus BF, right? So now if I just write down the dimensions here. So WF is of dimension 4 cross 9. It's a matrix of shape 4 cross 9, and this together is of shape 9 cross 1, correct? And this bias will be of shape 4 cross 1, because we have 4 neurons, we'll have 4 biases, right? So this here, it's a multiplication, right? This is a matrix multiplication. 4 cross 9 into 9 cross 1. So the resulting output will be 4 cross 1, right? So I'll write it here, 4 cross 1, and we are adding the bias 4 cross 1. So the resulting output will be again 4 cross 1. So this gate GF, so let me just scroll up here. This gate GF here is a vector of dimension 4 cross 1, right? So this is a vector of dimension 4. And remember, for LSTM, this dimension should be same for all the gates. So if we get 4 cross 1 for forget gate, it should be same for output gate and also update gate. So keep that in mind. Okay. So that's compulsory for LSTM. Now that we have computed this forget gate here, right, we have applied the sigmoid function, right? So this is our forget gate. What we are doing a point-wise multiplication here. So if you just look at here, this is a point-wise multiplication with the previous cell state, right? So what is that? We are taking this G, yes, forget gate. We are doing point-wise multiplication with previous cell state CT minus 1, right? So this is it about the forget gate. So if you have made it till here, congratulations, you have completed about forget gate. Now we will see how this enables either to forget or not to forget, or to forget partially some information from the previous cell state. So we know that this is a cell state, right? Or we can also call it as a memory cell. Now let's say, since we have the sigmoid function for calculating GF, the outputs will be between 0 and 1, right? Because sigmoid will squish the inputs between the range 0 and 1 in the output. Okay. So let's say we have got all 0.5s, 0.5, 0.5, 0.5 and 0.5. Why I have written this 4 times? Because GF is a vector of 4 dimension. Okay, so it's a 4-dimensional vector. So I have got all 0.5s in that gate, forget gate, right? Now let's say in my previous state CT minus 1, I have some values like 2, 4, 6, 8. Okay, why only 4? Because even CT minus 1 will be of the same dimension as of our hidden layer dimensions. So in our case, hidden layer dimension is 4. That's why CT, GT, GF, GO and GU, AT minus 1, CT minus 1, all will be of shape 4 cross 1. So you have to remember that. I will not repeat it again in the next steps. Okay. So now what we are doing point-wise multiplication with these two vectors. So I'll have this here 2, 4, 6, 8. So with the pointwise multiplication, what happens? 2 into 0.5 will be 1 because we are dividing by half, right? So 4 into 0.5 it will be 2, 6 into 0.5 3, 8 into 0.5 4. So what we are doing? We are forgetting about 50% of the information. From where? From previous cell state. Okay. So this forget gate here has authority to decide how much information should be let in order to compute our end result, which is CT. So in this case, in this example, we are forgetting about 50% of information, right? So suppose, what if we get all zeros here? 0, 0, 0, 0. It's possible, right? Because we have sigmoid function, values can range anywhere between 0 and 1. So if we get all zeros, we have the pointwise multiplication with 2, 4, 6, 8, and the resulting output will be all zeros. So what it means? It means we are forgetting everything. We are forgetting everything from our C t minus 1. From t minus 1 cell state, we are forgetting everything. So in my case, where I was explaining you something on the Magad kingdom, where Chandragupta Maurya will dethrone Dhanananda. So you can take that as an example. When we reach the sentence, later Dhanananda was overthrown by Chandragupta Maurya. So this forget gate will help us to remove Dhanananda from the context. Okay. So that's what it is. If we set all to zeros, we will forget that word Dhanananda from our context at this particular time step. Okay. Now what if the forget gate values all are 1? 1, 1, 1, 1. We have the pointwise multiplication again with the same CT minus 1. So what happens? In this case, we are not forgetting anything. We are not forgetting at all. We just want to pass in the information from CT minus 1 as it is to CT. Okay. So this is about forget gate. Hope this is clear. I know it's a bit complex, but if we split it out in multiple steps, it will be clear. That's why I'm taking so much time and going so slow in explaining you guys how this works, and I'm also explaining you how the forget gate has authority to forget something, forget everything, or not to forget at all. Okay, hope this is clear. Now we are done with forget gate, right? Now we will come to update gate. So we are dealing with update gate now. Okay. So what happens in update gate? This actually has three stages. Three stages, or you can call it as three steps. Okay. So in our previous step, in our forget gate, we will forget something. Usually we will forget something. That's why it's called as forget gate. So since we have forgotten something, we may need to add some information at this particular time step t, right? So what is that information? That is called as C bar t. You can see that here, right? So let me change the color so that you can see this is C bar t, right? So how it is calculated? So C bar t is a tan h. Activation is tan h on. We will have its own weights associated. So WC multiplied by this AT minus 1 comma XT, and we will have the bias BC. Okay. So this C bar T here is called as candidate for replacement. Candidate for update or replacement. Okay. Now we have calculated what kind of information we need to update since we have forgotten something in our forget gate step. Now we have come up with some candidate we want to update at this particular time step t. Okay, but this is the first step, or you can call it as the first stage. In first stage, we calculate the candidate for update. In our second stage, we actually calculate something called as GU. This is update gate. Right? So how do we calculate this? I will tell you why we calculate this also in next step. Okay. So how do we calculate this? We have a sigmoid function here, right? So this is our, this entire thing is our GU. Okay, here it is denoted as IT. Now I am calculating GU. Right? So how it is? It is sigmoid of, it will have its own weights associated with it. That is WU multiplication with AT minus 1 and XT plus its own bias BU. Okay, so this is our update gate. Fine. So you can see it here clearly. We have tan H for computing the candidates for replacement or update, and this particular thing for computing update gate GU. And then we have another thing by taking two of these as input. What are those two things? The candidate for replacement and the update gate. We are again doing a point-wise multiplication, right? So this, what we do in this third step, we do point-wise multiplication of GU with C bar T. So what it is? Actually, there is no name to it. Okay, there is no name given to it. So, but what happens here? This again GU, it's a sigmoid activated value, right? Sigmoid activated value, correct? And the range of output will be between 0 and 1. So again, this will act as some filter so as to determine how much of the candidate information should be passed through in order to take it as CT. Okay, so let's say we have some information 3, 6, 9, 12. Okay, so out of this, how much information we need to pass in? So this will be acting as a filter here. GU will be acting as a filter on the candidate for replacement at this particular time step. Okay, hope this is clear. Right? Now, once we get this, we have a pointwise addition on the output of the forget gate with this particular output on the update gate. Right? So what is it? That will give us candidate or the cell state at particular time step t. Right? So we will end up updating the memory cell. So how it is done? If you look at that figure CT, so we take the output from the, we take this entire thing and we take this entire thing and do a pointwise addition, right? So what are those two things? Those two things are GF multiplied with CT minus 1, right? So that is, let me write it, it's GF pointwise multiplication with C T minus 1, and then we are having pointwise addition on this stuff, GU pointwise multiplication with candidate at step T, time step T, right? So this is our candidate, or you can say context for time step T. Okay, so hope it is clear till this time, till this particular step. Now you can work out the dimensions by yourself, or let me walk you through quickly. So this AT minus 1 XT stacked together again will give us 9 inputs, and hidden neurons, we have 4 number of neurons in the hidden layers. So again, it will follow the same dimension calculations. So 4 by 9, 9 cross 1, again biases will be 4 because we have 4 neurons at each of the hidden layers. Okay, so again we will end up with the same consistent shape, that is GF is of 4 cross 1 dimension, so is GU, it is also of 4 cross 1 dimension. Candidate for replacement is also of 4 cross 1 dimension, and also CT minus 1 is of 4 cross 1 dimension. So CT, candidate, the context at that particular time step is also of 4 cross 1 dimension. Okay, hope this is clear. So if you guys have any doubts with the dimensions, working out with the dimensions, you can just rewind it and then check how I computed for forget gate. Okay, now we have covered two steps in detail. One we are done with forget gate, other one we have done with update gate. Now it's simple. All we have to do is work with the final step here, that is output gate, right? So we represent output gate as GO. How do we calculate it? The input for this will be, we take CT from here. Okay, so let me just highlight this. So we will have CT here after this everything. After these two steps, we will have CT here. We will take that CT and apply tan H first. Okay, so let's not write GO right now. So this has multiple steps, the output step. So the first step is to apply tan H on CT. So how did we get CT? We got the CT in our update gate step, correct? So this is our tan H on CT. Next, what we do pointwise multiplication on sigmoid of this stuff. So this is nothing but output gate. Second is, we calculate output gate as sigmoid of the weights associated with output gate. Again, A t minus 1 comma xt plus B O. So this is output gate. Then what we do, AT, or the activation at this particular step, will be pointwise multiplication of output gate and this tan H of CT. Okay, so this is how we obtain the activation at this particular time step T. Now there is another thing, the same activation AT can be given as output here. It actually depends upon the task that we are dealing with. And on top of this AT also, you can have some activations applied in order to calculate this particular output here. So let me just call it as y hat t. So prediction at this particular time step t. So if I just take ht, it may get confused, but if you want to have an output at this particular time step or predictions at this particular time step, you can take this AT, have some activation functions applied on it, and then treat this as prediction at that particular time step t. Okay, so that's it, guys. I hope I have explained it clearly. I have not wandered away or done any mistake. I have gone very slowly. So before concluding, let's see how this helps us in maintaining a long-term context. Okay, so again, let me just copy this diagram here. Right, so we have our CT minus 1 and CT here. So let's say we want to maintain the context as it is from previous time step at current time step. How can we do that? So let's say we have some values in CT minus 1, 1, 2, 3, 4. Okay, so we want these 1, 2, 3, 4 to be passed as it is to CT. We do not want any updates, or we do not want to forget anything from the previous time step. We do not want to forget any context from the previous time step, and we are not interested in adding any new context at the current time step. How do we do that? So while training, we need to make sure that this forget gate, so it's a this forget gate here, we have GF here, right? So sorry for that color. So we have GF here, right? And we are doing a pointwise multiplication. So at this time step, we want GF to have all ones, so that if we multiply with CT minus 1, the result will be CT minus 1 values only. So we are good till here. But what about here? We are doing a pointwise addition, right? So we want the product of this output gate and the tanh functions to be 0. So we want all zeros here, so that addition of 1, 2, 3, 4 with the zeros will result in again 1, 2, 3, 4, which will be our CT. Okay. So you see here, we can, if we repeat the same step with the similar values for hundreds of time steps, we will be successful in maintaining the context from time step 1 till time step 100. So we are not bothered about vanishing gradients issues here. So due to vanishing gradients in simple RNNs, we are forgetting the contexts which have occurred much earlier in our time steps, right? So that problem will not be raised here, right? So that's it for this video, guys. Hope it's clear. And since it has been a long video, that's why I have broken this LSTM series into 3 parts, right? So in my first part, I have set the stage as why we need LSTM. In my second part, I have explained the architecture. I have given you the overview. And in this third part, I have explained you in detail with complete math involved in it, right? So hope this is clear. If you have any questions, please reach out to me via comment section. If you guys have not subscribed to my channel, please do subscribe. And if you like this video, please give it a thumbs up and share it with your peers. Okay. So that's it for this video. Till we see in the next video. Happy learning. Bye bye.